In this lesson, we're going to be talking about one type of chemical analysis called quantitative analysis. Now, quantitative analysis is the determination of the amount or concentration of a substance in a sample. Now, this is what we've been doing with our stoichiometry calculations throughout the past chapter, where we've been taking mass or moles and converting it into mass or moles of other substances based off of our balanced chemical reactions. The type of quantitative analysis that I want to talk about here are for three specific types. That is titration, combustion, and gravimetric analysis. Now, we are not going to focus on combustion. We're going to look at titration and gravimetric analysis specifically. If you would like to read more on combustion analysis, there is a great section in your textbook, but we will not be going through that and you will not be tested on that. So our first type of chemical analysis is known as titration. This is typically seen in neutralization reactions where we have an acid and a base reacting together to create a salt and water. And typically we have two solutions. One solution has known volume and known concentration, while the other has known volume but unknown concentration. And the purpose of a titration is to determine that unknown concentration. So the solution that has known concentration and known volume is known as our titrant. Our analyte then is our solution of unknown concentration and known volume. So we will always titrate our titrant into our analyte in order to determine the concentration of the analyte. Now we know when this reaction is completed in a titration because we reach something called an endpoint. The endpoint is the point in the reaction where everything is used up, all of that analyte is reacted, and the acid-base reaction is complete. We've taken all of that acid, reacted it with enough base to make just salt and water in our solution. If you're in the lab, you would see this by a color change noted by an indicator solution. So sometimes we see color changes from clear solutions to pink, yellow to blue, green to yellow. There's even an orange to pink. There's a bunch of different indicators that can tell us the endpoint of those reactions, because typically they're between two solutions that are both clear, so there's no way to tell when the reaction is done unless we have an indicator. Now, when we're looking at titration calculations, which I have an example for right here, we know the volume and we know the concentration of our titrant, and we know the volume of our analyte. And the idea is that we're finding concentration. So concentration, so for this example here, we're finding the concentration of the acid, which has units of moles over liters. Well, liters is already known, and we know from concentration, back in our chapter about concentration, if we know moles and we know volume, we can find the concentration. So our volume is already known for this acid. Okay, it's given right here, it's 50 milliliters. What we don't know is the mole value, so the moles is what's actually unknown. But what we do know, I'll change this color so we know our differences, is we know the volume and the concentration of our titrant of what was being titrated in these solutions. So we can use that to find the moles of the barium hydroxide in this example, or whatever has known volume and known concentration, so our titrant. Okay, we can use that to find the moles of that substance. And then with our balanced reaction, which we have here, we can go between the titrant and the analyte based off of their mole-to-mole ratios from the balanced equation. So let's look at this problem. So the endpoint in a titration of a 50.00 milliliter sample of HCl hydrochloric acid, one of our strong acids, was reached by addition of 45.87 milliliters of 0.350 molar barium hydroxide. And we want to know what the concentration is of the acid, of the HCl. I want to know its concentration. I'm given the balanced reaction here, so we can use that for our mole-to-mole ratios. Our first task is to find the moles of barium hydroxide. So what we're going to do to find that is we're going to take our volume, which I'm going to convert first to liters because we know if we're working with molarity, we have to use liters, not milliliters. So we're going to take that 0.04587 liters of barium hydroxide, and we're going to multiply it by its molarity. Now, molarity has units of moles per liter, meaning it can be used as a conversion factor to go between volume and moles. Okay, this is just like what we see on a concentration triangle or molarity triangle. If I want moles, I take my molarity and I multiply it by my volume. So we're going to put 0.350 moles of barium hydroxide on top. And we're going to put 1 liter of barium hydroxide on the bottom. So this allows us to cancel out our liters, and we're left with moles of barium hydroxide. Now that we have moles of barium hydroxide, we can then convert to moles of HCl using our balanced equation. So we put the moles of what we don't want on the bottom, which is 1 mole of barium hydroxide. The 1 comes from the fact that out front here is a 1. Okay, when we don't have a coefficient out in front, that means it's 1. And then we put our moles of what we do want on top, which is 2 moles of HCl. So that 2 comes from the molar coefficient out front of HCl. Now that we have moles of HCl, okay, we can then calculate what that value is, which is going to be 0. Do it over here. We're going to take 0.04587. We're going to multiply it by 0.350 and multiply that by 2. So I've just multiplied across here. I don't need to divide by anything because my denominators here are all 1. So my moles of HCl are 0.032109 moles of HCl. Now I'm not done yet because I still want to find the concentration of HCl, but it means we now know this value here, moles is now known, volume is now known of our acid, therefore we can take those two values, divide them, and find our concentration. So we're going to take our 0.032109 moles, divide it by our 50 milliliters, which we are going to convert to liters because molarity has units of moles per liter, not milliliters. Okay, so we're going to get that answer divided by 0.05000. So we get a molarity of 0.642 with sig figs. So we have 3 sig figs coming from our concentration of barium hydroxide. So our concentration of our acid from this titration is 0.642 molar HCl. So to review, we started with our volume of barium hydroxide. In order to convert it to moles of barium hydroxide, we had to use our concentration. Okay, remember our concentration can be written as moles per liter, meaning it can be used as a conversion factor between volume and moles or moles and volume depending on which way we need to go. Once we do that conversion, we're left with moles of barium hydroxide. If I have moles of one reactant, I can convert that to moles of any other reactant or moles of any other product in my balanced chemical equation, which is what I do in my second and my last step here, where I take the moles of HCl and moles of barium hydroxide and use those to convert to moles of HCl. Now that we have moles of HCl, we can divide that by the volume of HCl, which we know from the problem, but if you were in the lab, you would have that volume recorded on your data sheet. Okay, so we take that mole value, we divide it by our volume, making sure that volume is in units of liters, and we get a concentration of 0.642 molar for our acid. So that's how we typically see titration calculations. We have 2 volumes and a concentration, and we use the multimole ratio in order to convert between those two. So we use our knowledge of concentration back from our previous chapter. We use that knowledge to now solve and go between two different chemical species. So we're still using our mole to mole ratio to connect one part to the other. The other type of chemical analysis that we're going to see often, and which we have seen multiple times in previous lessons, is called gravimetric analysis. And in gravimetric analysis, this is when we have some sort of physical change that happens between when our two reactants come together and react to form our products. So this is most likely seen with precipitation reactions, where we go from two solutions that don't have solids in them, and then when we mix them together, a precipitate forms. So I have the precipitation reaction between magnesium sulfate and barium nitrate here. I have the balanced equation up as well, so that is all there for us to use. And the question is asking us to take 0.730 grams of magnesium sulfate, which is dissolved in water, and reacted with excess barium nitrate. So my two reactants here, I know that my mass of this is 0.730 grams. This one is excess, meaning I have enough of it to react fully with my magnesium sulfate. And what we want to know is when these two react together, what is the mass of the solid that is formed, which is barium sulfate. So we want to go from mass of magnesium sulfate to mass of barium sulfate. So we know that if we have masses, we can find moles, and if we have moles, we can find masses, because we just have to use our molar masses to convert. Okay, this is very similar, if not the exact same thing, that we've been looking at in our previous problems when we started to introduce these stoichiometry calculation problems. So for this problem, we are going to start with our 0.730 grams of magnesium sulfate. Okay, and what we're going to do is convert that to moles, because once I have moles of any reactant or product, I can convert between any other reactant or product in my balanced equation. So we always want to make sure we are converting to moles if we want to convert between two different chemical species. The only way to go between two different chemical species is to use a mole to mole ratio. So we have 0.730 grams of magnesium. Magnesium sulfate, sorry. I know that in 1 mole of magnesium sulfate, I have 120.37 grams of magnesium sulfate. That is just the molar mass of magnesium sulfate from the periodic table once you add up all of those molar masses. So that cancels out our grams of magnesium sulfate, and I'm left with moles of magnesium sulfate. So now, since I want to find the mass of my precipitate, I can use my balanced equation up here to convert between magnesium sulfate and barium sulfate. So from our balanced reaction, we know that 1 mole of magnesium sulfate reacts to create 1 mole of barium sulfate. Okay, our coefficients out in front are all 1, so it's a 1-to-1 mole ratio. I put my moles of magnesium sulfate on the bottom because I want to get rid of it. I want to cancel it out. And I want to be left with barium sulfate, which is why the moles of that value are on top. Once we have moles of barium sulfate, we can now convert to mass using our molar mass of barium sulfate. So we know that 1 mole of barium sulfate has 233.4 grams of barium sulfate. So let's do this math. So we take 0.730. We're going to multiply it by 233.4. So I'm just multiplying everything on top together. And then I'm going to divide by everything on the bottom here. So that's just going to be divided by 120.37. Everything else is a 1, so we don't need to account for it. So we get our mass of barium sulfate to be 1.415486 grams of barium sulfate. Now with sig figs, our sig figs coming from our mass of magnesium sulfate, this becomes 1.42 grams of barium sulfate. So that's what we are going to have. So if I take 0.73 grams of barium sulfate and I react it with enough barium nitrate, my precipitate that forms will have a mass of 1.42 grams. Let's do one last practice problem before we end this lesson. So what I want you to do is to just quickly pause your video, look at this problem, set up a plan, think about what steps you would take in order to solve for the two values that we need for this problem, number of moles and mass of gallium chloride. Okay, take a second, pause the video, think about what you would do. If you're feeling confident in your work so far, try it on your own and come back and see how we work it out. So this problem is going to be set up very similar to our titration problem, except in that we have volumes and molarities. Okay, except it's not a titration, it's a type of gravimetric analysis because we have, gas being formed from this reaction. So we have a physical change occurring. So we have two values that we want to find here, the number of moles and the mass of gallium chloride that are formed. Okay, so we're going to start this off with our volume, just like we did with our titration. Okay, we're going to start with our volume, that 2.6 liters. It's already in liters for us, which is great. That's liters of HCl. And we're going to convert it to moles using our concentration. Our concentration has units of moles per liter, so we can use that as a conversion factor. So we have 1.44 moles of HCl in 1 liter of HCl. So that conversion automatically cancels out our volume unit and we're left with moles of HCl. Once we have moles of any reactant or product, we can convert to any other reactant or product in our balanced equation, so we can convert to moles of gallium chloride. So we know from our balanced equation that that ratio is 6 moles of HCl on the bottom because you want to get rid of the moles of HCl, and we have 2 moles of gallium chloride on top because that's what we want to be left with. Now, because one part of our problem asks us for the number of moles, I'm going to stop here and solve real quick. So we're going to take 2.6, multiply that by 2 and by 1.44. So I'm multiplying the top portions together, and then I'm going to divide by 6. And we get 1.248 moles. Now, with sig figs, this is going to be 1.2 moles of gallium chloride. The next part of this problem now asks us to find the mass of gallium chloride, which we are fully capable of doing. We've done this multiple times in other chapters, where if we know moles, we can find mass by using our molar mass. So we take our 1.248 moles of gallium chloride, and we're going to multiply it by our molar mass, which we can find from our periodic table. We put moles on the bottom so that they cancel, mass on the top so that we're left with grams. So we're going to take that value, that 1.248, we're going to multiply it by 176.07. And we get a mass of 219.73536 grams of gallium chloride. Now for sig figs, this would come down to 2.2 times 10 to the 2 grams of gallium chloride. Why do we do that? Because when we round this, this is going to be 220. Okay, and then we want to omit, we want to have no ambiguity, so we want to put it into scientific notation, so that would be 2.2 times 10 to the 2, so that we don't have that extra 0 at the end that's ambiguous.